So, thank you very much. Good morning, everybody. It's my deeply honored to be here and to give this keynote lecture today. And in my keynote lecture, the topic will be, this is not the right one. Could you? So sorry for this technical issue. Now I'm here. So again, I'm very pleased to give this keynote lecture today. And as you can see, the topic of my keynote lecture are digital twins of roads. And especially, I would like to highlight the role of geometric-semantic as-is models for these digital twins. So let me first introduce and motivate why is our research focused on digital twins of roads. And to explain this, I brought some numbers. These are numbers from the official German transport statistics that is updated from the Federal Ministry of Transport every year. And among other indicators, it also shows the performance of different modes for the transport of goods or the freight transport. And what you can clearly see is that the road outperforms all other modes, railways and waterways, by far for the transport of goods. And that's very important because roads are the backbone, as you can see, of the economy, because the transport of goods is very important for the economy. However, also roads are very important. They face some challenges. And first of all, we have an increase of traffic year by year, causing traffic jams, for example. Also, we have an increasing load, so the vehicles become heavier. This impacts the condition of the road, of course. That means the durability is a problem. Roads are prone to recurring damages. And of course, repairing these damages, maintaining roads needs a lot of resources that are limited and should be used in an efficient way. However, besides these, let's say, traditional challenges of roads, we have also some new demands. Roads should support autonomous driving, electric mobility in future. And of course, roads should impact or should also contribute to sustainability, for example, to energy production. And this finally leads to the question, how can roads meet all these challenges and future demands and at the same time continuing to fulfill its essential role? And our answer to this question is a consequent digitalization of the road systems following the concept of digital twins. Before I go into details what we mean by digital twin, let me first define what we mean. We heard already we shouldn't talk too much about digital twins and define what it is. However, as you know, if it comes to digital twins, there is a different understanding among people what a digital twin really is. And in our case, I use a definition an official definition, again from the Federal Ministry of Transport in Germany. And it says, okay, a digital twin is a virtual representation of the real world system, in our case, the road system. But what's very important, it's a dynamic representation. So it changes over time because the real road also changes over time. And however, there's something very important. It's also a virtual representation of the causal relationships, because everything what impacts the road has also to be modeled. And this is important because on the right-hand side you see this figure, because therefore you need a lot of further data and models to be integrated in such a digital twin. So you need geospatial data, you need sensor data for capturing the condition of the road, you need environmental data, data from inspection, BIM data, and so on. And so a core feature of a digital twin, for me at least, is this integration part. Because all of this data is usually stored and managed in separate systems that are not connected so far. And there's also another feature for a digital twin. This is this bidirectional data transfer between the real world system and the virtual world system. Okay, having this in mind, let me now briefly introduce our research project. It's a CRC, a collaborative research center, in German SASBE+FR+BDT, on digital twins of roads. And this collaborative research center is a collaboration between two universities, the TU Dresden in Germany and my university, RWTH Aachen. And as you can see, we started this project in 2022. And it means a CRC, if we are lucky, we can do research for 12 years in 3 phases, each 4 years. However, we have to apply for each phase. And this year in March, we applied for the 2nd phase, and we applied successfully. So we have now 4 more years for research. And what you see in the middle, these icons, there are 20 icons. These are the sub-projects in the CRC, addressing a distinct problem when it comes to digital twins, starting from material-related questions, sensors, communication technologies, modeling, as well as sustainability or legal aspects. So it's really a huge project we have there, and dealing with all aspects across the digital twin. Okay, so what is basically the idea for this project? Okay, it's about creating a digital twin, but actually it's a basic research project. That means we are going to research the methodological foundations for setting up such digital twins. And that means, for example, on the left-hand side, the physical side, we deal with new sensors and sensitive materials. We need communication technologies for transferring data from sensors to the virtual systems. On the right-hand side, then we need, of course, a lot of models, information models, but also physical models for modeling the vehicle-tire road interaction, for example, because this impacts the road much. And also we have data-driven models for exploring the data, for having fast simulations in order to support decision-making for an optimized management of the road system. One of these models I would like to highlight now, because we think this is a key foundation of a digital twin. This is a geometric-semantic as-is model. Why this is the case? First of all, such a geometric-semantic as-is model is an information model. So we are able to store a lot of information about the geometry, topology, semantics, as well as alphanumeric attributes. But coming back to my definition, it's also very important to integrate further data. So it allows to integrate sensors and sensor data, as well as location-dependent data, like, for example, the position of vehicles. And it's also able to visualize, for example, the results of numerical simulations. And let me go into a little bit more details about that. And I will start how to create such a model. And maybe Peter likes this slide, because I know Trimble is also manufacturing some of the technologies seen there, because digital twin has to be a virtual representation of a real system. And that means also it has to represent the as-is condition of the system. And how do we get the as-is condition? Therefore, we can use modern reality capturing technologies like laser scanning, drones, or mobile mapping systems, rather than using design data, for example, like plant models or something like that. And in result, we have such a high-resolution 3D point cloud, which can use for visualization purposes, of course. However, these point clouds also include a lot of information, explicitly the geometric information. You can get from this point clouds the shape, the dimension of the road, can measure lengths, angles, volumes, and so on. However, what's also in these models, implicitly, if you look on this point cloud, you can clearly see the roads, road markings, the vegetation, and so on. That means these point clouds also include semantics. And that means what we can do using these point clouds is to create classes and assign to these classes attributes and store, besides the geometry, also some alphanumeric data. And furthermore, and this is very important, you can now use the semantics to connect the classes to further data. For example, to external databases, damage databases, and you can just use the semantics linking the objects to other databases. So it's really the basis for semantic linking. However, coming back to the point clouds, because the value of the point clouds go beyond just having geometry and semantics, because point clouds usually are captured in a georeferenced way. And that means the point cloud itself inherits a geospatial reference system, and also the models derived from these point clouds inherits this geospatial reference system. And that makes it possible to also link other data in a spatial way. That means, for example, sensor data or the results of numerical models can be linked to this model just by the location, by the spatial reference. Okay, I hope this sounds reasonable so far. But the question is now, what do we research? Because deriving such models from point clouds is feasible. However, in practice, the problem is that this is a very cumbersome task, and you need many manual steps to create such models, what makes it costly and time consuming. So the question is, how can we automate this process? And this is exactly what we are going to research, automating this process. And we call it scan-to-twin. You all know maybe the term scan-to-BIM, and now we call it scan-to-BIM because it's more or less the same. However, there's some differences. I will come to that later. So let me briefly introduce what we do in research. First, we structured the whole process to create such model, and this results in a multi-step pipeline starting from data capturing, as already shown. The second step then is the semantic segmentation. That means we assign a semantic class to each of the points. Then in the third step, we try to extract the geometry, for example, the center lines, the axis of the road, and both together, semantics and the geometry, is then used for creating the model. And as you can see on the right-hand side, for creating the model, however, we have to consider also the use case, because digital twins can have several use cases, and each use case has some requirements also for the models. And so we have to consider these requirements to create an appropriate model for the respective use case. Let me give you some more details or impressions from this multi-step pipeline, starting with the data capturing I already mentioned. Therefore, you can use modern reality capturing technologies emerged in the past years. We, for example, use LiDAR scanners besides airborne laser scanning data, and these drones are equipped with a LiDAR scanner, enables us to capture data from the roads very efficiently. And as a result, we have such point clouds like shown here, high resolution point clouds that can be used for the next step. And in the next step then, it's about the semantic segmentation. As you can see, now the point cloud becomes colored. That means in this step, each point is assigned to a semantic class, and therefore we have developed some algorithms, a coarse-grained and a fine-grained semantic segmentation using also AI to assign these classes to each point. Third step, then the geometry extraction. We also developed different approaches, different methods and algorithms for doing so, from semi-automatic extraction to data-driven, and we compared them, of course. But in this case, I don't want to go into much details because we will have a presentation in the next session. It's a special session on digital twins given by David Krampen, and he will explain especially how this rule-based geometry extraction works. Okay, and then finally, creation of the model. And as I already mentioned, it's very important to consider the use case. And therefore, on the left-hand side, we developed a multi-LOD concept. That means we split up, or we distinguish between the geometry and the semantics. And for each, we have different granularities. And this allows us to create models at the end that have different level of detail. And this enables us to, it's not working well, but this enables us to support different use cases from micro scale to macro scale. That means from pavement monitoring was more or less on the material side up to driving simulations, because all of these use cases have different requirements for the models itself, and this can be described by this LOD concept. Okay, I said it's a basic research project, that's true. However, for practice, it's also important that we can export these models in some standard formats or standard data models, like, for example, IFC from BIM, or CityGML from geospatial modeling, or LaneLab. And so we also investigate how to do that, how we can export the models in these formats to really support then different applications. And last but not least, the goal of our projects is to deliver a model for a digital twin. So here you can see the model. Cannot see very good. However, you have an impression how this model looks like, and what you see there is also a sensor system and the vehicles driving by. And the goal is, of course, to integrate now this model into a digital twin, but I will give you some more impressions in a minute about that. Because to show that it really works, we prepared a so-called showcase. That means it shows how our geometric-semantic model can be used, and besides other data, to support a specific use case. And in this case, it's a use case about pavement monitoring. And we integrated data from further sub-projects, starting with vehicle data. We have one sub-project that uses data from vehicles, from dampers, from the tires, to sense the condition of the road, for example. We have also a project dealing with pavement data. So we have installed a weigh in motion system in a highway, giving us data about the loads of the vehicles. Then in the middle, you can see our GSM, our geometric-semantic model. Another project deals with vehicle position. So it's about tracking of vehicles and position estimation. All this data is also integrated. And last but not least, we have a couple of projects dealing with fast simulation, data-driven simulations, in order to do real-time simulation, in this case of the pavement response, based on the data from the vehicles and the geometry from the geometric-semantic model. Okay, and how this looks like, we have prepared a small video showing what we have done so far. It starts with the physical side. As mentioned, we had the opportunity to install a weigh-in-motion system on a German highway. So here you can see how the system was installed. These are the bars, the sensor bars of this weigh-in-motion system. We then also scanned the whole scene, this highway section, with a terrestrial laser scanner, and this 3D point cloud is then the basis for our geometric-semantic model. we also captured a lot of data. Of course, we captured first data with our way in motion system. Here you can see again the 10 sensor bars of the way in motion system on the German highway. And this is how it looks like in the geometric-semantic model, the model itself, but also the sensor bars. And you can see the tires of the vehicles that are also modeled. And we also captured data by vehicles. So by these sensors of vehicles, you can see it's a Mercedes-Benz, so it's a German project, so a German car. It's quite clear. And we use this data also to get some information about the condition of the road. In this case, they drive the same highway section. We have the way motion system installed. What can we do with that data? Of course, we can first of all analyze the loads and create this load tracks of different vehicles, so you know what is the load at a specific point in the model. And to do better, we also create a kind of physical lab model of the same highway section. Here you see the small cars, and in the middle that black pattern, this is a pressure map. So it's the same as the way in motion system in the real system here in the model system, and it helps us to do more research on it. And here you can see the vehicles and the position estimation. And this is very interesting what you see here. This is the result of a finite element model. Was a little bit quick, but I go on because we have a surrogate model that models or that simulates what is the impact, the deformation inside of the road based on the sensor data. And this is done in real time and can be depicted based on the roads. And at the end, what you could see, we do it now more or less in the lab or on this highway section, but in the next phase, the goal is to do this also on a test track near Aachen, the Altenhofen Testing Center, and we'll prepare a whole track, a whole road with different sensors for going on to develop our digital twin. Okay, so I hope I'm in time more or less. Okay, so because I come to the end of my presentation, I hope I could demonstrate what we do in our project and especially what is the role of such geometric semantic as is models. And with that, thank you for your attention.
Presentation. So now we have time for the questions. Who has the questions?
Thanks for the amazing talk. I was wondering, with the different levels of detail, you went from the micro scale to the meso, or the macro. I was wondering, what size are the files then? If you've got perhaps